Till now we have seen DFS, many questions for which we have constructed DFS and NFS, but then I told you that whatever answers I have given you are the minimal DFS, which means if you construct a DFA on your own, you might not get the same answer which I got, but then I have got all the minimal DFAs because of experience, that's it. Now the question is, can we take any finite automata, any DFA, only DFAs, can we take any DFA and prove that this is the minimal, or that such a DFA can even be minimized? So that is called minimization. So if a DFA is given, then we can apply a procedure using which we can decrease the number of states in the DFA. It is also called as minimization of a DFA. So before going for minimization of a DFA, let's talk about how we can minimize it, or what are the properties that we need in the DFA so that it can be minimized. We want to talk about states and equivalence between the states. Let us say there are two states, one is P and other is Q. We say that these two states are equivalent, and these two states in a DFA can be replaced by a single state if the condition is, if P on seeing W, which means the state P on seeing any input symbol, on seeing any input string, so W can be any input string, if this one goes to final state, it implies that Q also goes to final state, one of the final states. If in case P does not go to final state, then it implies that Q also does not go to final state. Try to understand this. Now if I have two states, let us say PQ, when can I combine them into single state is, they both have to be equivalent. I say that P and Q are equivalent when P on seeing any input string, if it is going to one of the final states, implies that Q should also go to one of the final states. Need not go to the same final state, but then they should be either final state or non-final state. If P is going to non-final, then Q should go to non-final. So if any two states follow this property, then we can say that such two states are called equivalent. If length of W is, mod W is 0, then both states P and Q are called 0 equivalent. 0 equivalent. If length of W is 1, which means if I see a single symbol and if they are following this property, then I can say that both states are 1 equivalent. If length of W is 2, then I can say that both are 2 equivalent. In general, if length of W is n, then I can say that both these states are n equivalent. And finally, if for every possible W, if this is the property being followed by P and Q, then I can say that both these states are equivalent, and instead of having two different states, I can merge these two states into one, and I can decrease the number of states in the final answer. So why to use this equivalence property and 0 equivalence, 1 equivalence, 2 equivalence, I'll take an example and I'll explain you with that. So let us say this is the finite automata DFA. So we are going to minimize only DFAs, not NFAs. This is the final automata, which is a DFA, and I want to minimize the number of states in this. First step is identify the start state and identify the final state. Now in this DFA, if there are any states which are unreachable or unaccessible or inaccessible, which means if there is any state if let us say there is a state like this Q5, and it is simply like this, A and B. If there is any state to which we cannot reach from the initial state, then we have to delete it. Step number 1 is try to delete all the states to which we cannot reach from the initial state. If you look at this diagram, all the states are reachable from initial state. Q0 is obviously initial state, Q1 is reachable, Q2 is reachable, Q3 is reachable, Q4 is reachable. All the states are actually reachable from the initial state. Now find out or draw the transition table, state transition table. Q0, Q1, Q2, Q3, Q4. A, B. Q0 on A is going to Q1 and Q0 on B is going to Q2. You can let us see the diagram. And Q1 on A is going to Q1 and Q1 on B is going to Q3. And Q2 on A is going to Q1 and Q2 on B is going to Q2. And Q3 on A is going to Q3 on A is going to Q1, Q3 on B is going to Q4, Q4 on A is going to Q1 and Q4 on B is going to Q2. What is initial state? Initial state is Q0. What is the final state? Final state is Q4. Therefore Q4 I am going to mark it like that, and wherever Q4 is there I just mark it like that. Okay. Now first point is try to find out the zero equivalent states, zero equivalent sets. Try to find out the zero equivalent sets. I'll write here zero equivalent sets. So zero equivalent sets are nothing but try to separate non-final states from final states. What are the non-final states? Q0, Q1, Q2, Q3. What are the final states? Q4. So initially this is the starting point. Start with zero equivalent. Zero equivalent states are, these are all zero equivalent and these are all zero equivalent, which means set of all non-final states and set of all final states. Once it is done, now we have to find out one equivalent states. Now take the previous states. For example, you have to see, let us say previous state is in the previous zero equivalents, take each one of them. See, all these states are zero equivalent, so we have to see whether they are one equivalent or not. Let us take Q0 and Q1, and let us see if they are one equivalent or not. If in order to see that, you have to take both of them and see where they are going on symbol A and symbol B. If you see Q0, it is going to Q1, and if you see Q1, it is going to Q1. Both are going to the same state. And if you see Q0, it is going to Q2, and if you see Q1, it is going to Q3. In the previous state, in the zero equivalent state, Q0 and Q3 are in the same, or I'll just draw a diagram here and I'll show you. See this? Now I'm checking for one equivalence of Q0 and Q1. So go to the diagram and you just draw like this: Q0 and Q1, these two, Q0 and Q1, these two. Now these two have to be in the same state in the above state. In the above state, which is zero equivalent, Q1 and Q2 are in the same group and Q2 and Q3 are in the same group. Therefore you can say that Q0 and Q1 are one equivalent. Now let us say these two are one equivalent. Now we have to see if Q2 is equivalent with any one of them. So if we have to see if Q2 is equivalent with any one of them, if you have to see if Q2 is equivalent with any one of them, you can take either Q0 or Q1 and check with Q2. See this? I am taking Q0 or Q1. Q0 and Q2. Q0 is here, Q2 is here. Q0 is here, Q2 is here. Just check them. Q0 and Q2 both are going to Q1, which is there in the same state, and both are going to Q2. When they are going to same states, they are obviously equivalent. Therefore Q2 is equivalent to Q0. Since Q1 is equivalent to Q0 and Q2 is equivalent to Q2, therefore Q1 is equivalent to C. Already we know that these two are equivalent. Now we found out that these two are equivalent, therefore Q2 and Q1 are also equivalent. Now we have to check if Q3 is equivalent with any of these three. So you can take only one and you can check it. So you can take any one. Let me take Q2 and Q3 and check for the equivalence. So I'll take Q2 and Q3 and check for the equivalence. Q2 is where? Q2 is here and Q3 is here. Now see them. Q2 on A, they both are going to Q1, so on A it is not a problem, but on B, one is going to Q2, other is going to Q4. One is going to Q2, other is going to Q4. So both are going to different states here, different groups here. Since they are going to different groups, they are not in the same state, or they are not equivalent, one equivalent. Therefore, Q3 only is not one equivalent with the others. See, try to understand it. When I am writing one equivalence, I will be using the information only about 0 equivalent. When I am writing 2 equivalent, I will be using the information about 1 equivalent. You will understand this with more examples. I will solve more examples, don't worry. See, now I want to find out 2 equivalent states. In order to find out 2 equivalent states, again start with the same thing. This is also called as partitioning method. There is one more method called table filling method. I am not going to discuss it and it is very difficult. This one is pretty easy, right? Let us talk about 2 equivalent. Now already Q3 and Q4 are the only people in their groups, or are the only states in their groups, so there is nothing to do about them. They are saying that we are not equivalent with any states, so therefore we cannot combine Q3 and Q4 anymore. Now we have to decide whether we can combine Q2 and these three, Q1, Q2 and Q0. Now let us take Q0 and Q1 and see if they are equivalent or not. Q0 and Q1 and see if they are equivalent or not. Q0 and Q1. So these are the outputs I need to see. Now see this, Q0 and Q1 both are going to Q1 only, that is not a problem. Why? Because they are going to same state. Now on B, one is going to Q2, other is going to Q3. One is going to Q2, other is going to Q3. Both are in different groups. Whenever they are in different groups in the previous equivalence, in this equivalence they are not equivalent. Which means in one equivalent state, if they are going to different groups, then in 2 equivalent they are not equivalent. Which means Q0 and Q1 are definitely not one equivalent. Now what about Q2? See, Q0 and Q1 both got separated. I don't know whether Q2 is equivalent to Q0 or Q1. Where should I place? Whether here or here. So I'll just check it. Now let me see if Q0 and Q2 are equivalent. Q0 and Q2 are equivalent. In order to check it, if I have to check for 2 equivalent, go to the 1 equivalent and use this table. Q0 and Q2. These two. See this? On Q0 and Q2 on A, both are going to Q1, and on B, both are going to Q2. Therefore, definitely they are equivalent. They are going to same states. Definitely they are equivalent. So Q0 and Q2 are definitely equivalent. Now what about Q1? It got separated. What about Q3? It got separated earlier only. What about Q4? Yes, got separated. So now we know these states are saying that we are not equivalent with any other states, therefore we have to have at least these 3 states, and now I don't know whether these 2 are going to be in the same group in the 3 equivalent or not. Let us say 3 equivalent. In 3 equivalent, again I have to check Q0 and Q2 only. Now if I check Q0 and Q0 and Q2, again the same result will follow. See this? Both Q0 and Q2 are going to Q1 and Q2 only. Therefore, these 2 states cannot be separated, or they are just equivalent. Now check this. 0 equivalent, we got 2 groups. 1 equivalent, we got 3 groups. 2 equivalent, we got 4 groups. 3 equivalent, we got 4 groups, and all the groups are same. So continue this method until we get 2 states like this, where nothing will change from one another. If you even go for 4 equivalent, you will see the same thing. So on, go for n equivalent, you will see this, you will see the same thing, which means this is the final answer. So in the final DFA we should have only 4 states, and these 4 states are Q0, Q2, Q1, Q3, Q4. Now let us try to draw the diagram and show how does the DFA looks like. Now one state is Q0, Q2. Initially we had 2 states, now I am going to combine them as one state, and the other state is Q1 and the other state is Q3 and the other state is Q4. Okay, now look at this. Q0 on A is going to Q1 and Q0 on B is also going to Q1 only. Q0 on A is going to Q1 as well as Q2 on A is going to Q1. Therefore, Q0 or Q2 on A is going to Q1. Now, Q0 or Q2 on B is going to Q2 only. So, on B, check this. Q0 is going to Q2, therefore Q0 should go to Q2, and Q2 is going to Q2, therefore that is it, just B. Next one, Q1 is going to Q1 on A and Q1 is going to Q3 on B, and next thing, Q3 on A is going to Q1 and Q3 on B is going to Q4. Next, Q4 on A is going to Q1 and on B is going to Q2. So the initial diagram, this is the final diagram. So you can understand one thing, even though there are many states in the initial diagram, they can be states can be decreased if you find out some few states which are equivalent, and then instead of having 2 different states for all the equivalent states, you can have 1 state. Let us say if there are n states which are equivalent, for all those n states we are going to have 1 state in the final diagram. This is the minimization procedure. Now we shall try to minimize this DFA. This is the DFA, okay, and that is the table which I have formed from this DFA. So let us assume that this is the question given, or you can even assume that is the question given. Both are same. This is the state transition diagram and this is the state transition table. If any state transition diagram is given, then better you convert it to state transition table, because minimizing from table is easier compared to minimizing from the diagram, or you can go in any way you can want. Now first of all, you have to observe one thing. First thing is, if there are any states which are not reachable from initial state, you remove them. Let's take Q1. Is it reachable from initial state? Yes. Let's take Q2. Yes. Let's take Q3. Q3, there is no way anyone could reach Q3. Therefore, I am going to remove Q3 and all the transitions incident on it directly. I am going to remove Q3. So Q3 is not going to be there in the final answer. Now, what about Q4? Is Q4 reachable? Yeah, I think Q4 can be reached via Q6. And what about Q5? Is Q5 reachable? Yes. What about Q6? Yes. What about Q7? What about Q7? Yeah, it is reachable via Q4. Yes. So everything else is reachable. Only state which is not reachable is Q3, and it has been removed. Now, what is the initial state? Q0. What is the final state? Q2. So just for the sake of convenience, mark Q2 wherever it has occurred. Q2. Okay. Now I am going to erase this and we shall work out with that table. It is no longer required. Once you have designed the table, state transition table, diagram is not required. Okay. So first step is we have to find 0 equivalent states. What are the 0 equivalent states? It is nothing but divide entire states into 2 groups. One group should contain all non-final states and other group should contain final states. 0 equivalent is nothing but Q0, Q1, Q4, Q5, Q6, Q7. Q0, Q1, Q4, Q5, Q6, Q7, and Q2 is the final state, just separate them. Next thing is you have to find one equivalent. In one equivalent you have to find out whether these zero equivalent states are still going to remain in the same group in the one equivalent or not. Those who remain in this same group are said to be equivalent. Now let us compare Q0 and Q1. Q0 and Q1, these two. Q0 and Q1 on 0 are going to Q1 and Q6. Q1 and Q6 are in the same group, therefore it is not a problem, it is not creating any problem. Now see this, on 1 Q0 is going to Q5 and Q1 is going to Q2. One is going to non-final, other is going to final. So Q5 is here and Q1 is here. So whenever they go to different groups in the previous equivalence, they are no more equivalent in the current equivalence, which means Q0 is separated from Q1, and I don't know who are going to join Q0 or Q1. Let's check it later. Okay, fine. So we have checked Q0 and Q1. Next thing is check Q0 and Q4. Let's take Q0 and Q4 and check it. Q0 and Q4, these two. Okay, so Q0 on 0 is going to Q1 and Q7. Q1 and Q7 are in the same group. See, don't see this when I am discussing about one equivalent. Don't see the partially formed groups of one equivalent. When we are working on one equivalent, we will always be working from 0 equivalent and this table. Now if you see Q0 is going to contain Q0 and Q1, and see Q0 and Q4 are going to Q1 and Q7. Q1 and Q7 are in the same group, and Q5 and Q5, obviously Q5 and Q5 are in the same group because they are the same state. Therefore Q0 and Q4 are one equivalent. Next let us say Q5. I want to check Q0 and Q5. So if you check Q0 and Q5, it is Q1 and Q2. Different groups. Therefore Q5 is not equivalent with Q0. So Q5 I cannot write it here. Now let me check with Q1. Let me check Q1 and Q5 so that I'll see whether they can be written together or not. I'm checking Q1 and Q5. Now if we say Q1 and Q5, they are Q2 and Q6 and Q2. Q6 is here, Q2 is here. Therefore it is not even equivalent with Q2. So Q5 is going to be a separate state. Why? Because it is not equivalent with Q1 or it is not equivalent with Q0 or Q1. Now let us say Q6. What about Q6? Let us check Q0 and Q6. You need not draw the lines to do this. I just wanted to explain you so that I am drawing the lines. You should be able to directly look into the paper, and then using fingers you should be able to do it. Don't draw the lines. Okay. Q0 and Q6, they are going to Q1 and Q6. Yes, Q1 and Q6 are in the same group. And Q4 and Q5, yes, Q4 and Q5 are the same group. Don't look at this group, this one, look at this one only, right? So since they are in the same group, they are equivalent. So Q0 and Q6 are equivalent. Therefore I am going to write it in the Q, this one. And next one is Q7. Let me compare Q1 and Q7. If you see it, Q0 and Q7, they are going to Q1 and Q6. That is fine. But Q5 and Q2, which are different, therefore it has to be separated. So Q0 and Q7 are not equivalent, so I should not write it in this group. Let me check it with Q1 once. Now let me check Q1 and Q7. Just see this. Q1 and Q7 are going to Q6 and Q2, same states. Therefore they will always be equivalent. If they are going to go to same state, they will always be equivalent. So Q1 and Q7 are always going to be equivalent, and Q5 is going to be alone. See this? So in the first 0 equivalence we got two groups, non-final and final. In one equivalence we got 4 groups, 1, 2, 3, 4. And in the first one it is going to contain Q0, Q4 and Q6. It means that all these 3 states are one equivalent. it means that all these two states are one equivalent. What does this mean? If you give any string of length 1, all these states either go to accepting state or go to non-accepting state. These two states, if we give any one length string, either they will go to non-accepting state or accepting state. Now let's talk about two equivalent. See, whenever you find any group with a single element, you need not process it again because we cannot separate them, so they are already separated. Okay, now let us see this one, Q0 and Q4. Let us compare Q0 and Q4 to find out if they are two equivalent or not. Q0 and Q4, right? So if you look at them, they are Q1 and Q7. They are going to Q1 and Q7. So Q1 and Q7 are in the, oh, you have to look at this, Q1 and Q7 are in the same group, no problem, and Q5 and Q5 obviously the same state. So see this, Q0 and Q4 are going to Q1 and Q7. So when you are talking about two equivalent, you have to look at only one equivalent. You have to look at only this one, not the previous one. Okay, now if you see Q0 and Q4, they are going to Q1 and Q7, no problem, they are in the same group, and Q5 and Q5, which is in the same group. Therefore Q0 and Q4 are equivalent. Now let us see Q0 and Q6. Q0 and Q6. Right, so Q0 and Q6 are going to Q1 and Q6. So Q1 and Q6, obviously they are from different groups in one equivalent, therefore Q6 has to go out. Now let us compare Q1 and Q7. If I compare Q1 and Q7, they are going to same state. See, Q6, Q6, Q2, Q2, so they can never be separated. They are always equivalent. Couple for life. Okay, fine. And now let us talk about three equivalent. In order to talk about three equivalent, we have to look at two equivalent only. So don't go to one equivalent or zero equivalent, just look at this one and you have to answer it, right? Let us see if Q0 and Q4 are equivalent or not. If in order to check for Q0 and Q4, Q0 and Q4, Q0 is going to, Q0 and Q4 are going to Q1 and Q7. Q1 and Q7, they are in same group. Q5 and Q5 and Q5, they are in the same group. Therefore, they cannot be separated here also. So Q0 and Q4 are even three equivalent. And this is already same. And Q1, Q7, I have already told you that they are couple for life because they are always going to same one. See this, Q1 is going to Q2, Q6 and Q7 is going to Q2, sorry, Q7 is going to Q6, Q2, Q6, Q2. They are always combined. They can never be separated, right? And even if you go for 4 equivalent, you will get the same. See, if 2 equivalent and 3 equivalent is same, even if you go for one more, you will get the same. Even if you go for 5 equivalent, you will get the same. Even if you go for infinity, they will get the same. Which means for every possible input, Q0 and Q4 are going to be in the same state, Q6 and these are going to be in same state. So in the initial diagram, if there are 8 states, the minimal DFA will contain 1, 2, 3, 4, 5 states. So we have minimized the DFA from 8 states to 5 states. This is the answer. And let me construct the DFA and even show you this. So if these are the final number of final states in the DFA, let me show you the DFA itself in terms of state transition diagram. So state transition diagram is going to look like this. Q0 and Q4. Q0 on 0 is going to Q1. So that group is Q1, Q7. Q1, Q7. They have to be together, right? So Q0 on 0 is going to Q1. And Q0 on 1 is going to Q5. This is 0, this is 1. And Q1 on 1 is going to Q6. Now Q1 and Q6, see this Q1 and Q7, Q1 on 0 is going to Q6 okay, and Q1 on 1 is going to Q2. Let us write Q2 somewhere. So where is Q2? The final state, it has to be somewhere. So Q2 is the final state. So Q1 on 1 is going to Q2. Now next one is, see, I think we have to get 1, 2, 3, 4, 5, 6 states. In initial there were 8 states and we have to get 6, which means Q0 and Q4 is combined and Q1 and Q7 are combined. Therefore the answer has to be 6 states, not 5 states. 1, 2, 3, 4, 5, 6. You have to even include Q2 also. I forgot to include it. Okay. Now this one is complete. This one is complete. Now let's see Q6. Q6 on 0 is going to Q6 and Q6 on 1 is going to Q4. If it is going to Q4, it will go to Q0 and Q4. Next, this one is complete. What about Q2? Q2 on 0 is going to Q0 and Q2 on 1 is going to Q2 itself. Next one, Q4. Q4 on 0 is going to Q7, yes, and Q4 is done, because see, once if I am done with Q0, Q4 is the same, and once you are done with Q1, Q7 is the same, right? So next one is Q5. Q5 on 0 is going to Q2 and Q5 and 1 is going to Q6. So once you are done with Q0, you need not write again for Q4. Once you are done with Q1, you need not again do it for Q7. So this one is complete, this one is complete, this one is complete, all are complete. So this is the final diagram. So how many states did we get? 1, 2, 3, 4, 5. I think one more state should be there, 6. So is there any state missing? Q0, Q4, Q6, Q1, Q7, Q5, Q1. Oh, it has to be Q2, it is not Q1. Fine. So it is just 5 states, not these many states. Okay, so this is the final answer. Now this question is given in one of the previous GATE papers. Now we have to minimize this DFA. Always remember, first rule is, if any state is not reachable from the initial state, you have to delete it. Is Q1 reachable? Yes, reachable. Is Q2 reachable? Yes, reachable. Is Q3 reachable? No, Q3 is not reachable. Therefore, delete Q3. Okay, so this is the diagram. Now for the resulting diagram, you just give the transition table. See, transition table is easy. If you can do it directly, yes, go ahead. But I am used to transition diagram. A, B. Q0 on A is Q1 and Q0 on B is Q0 itself and Q1. Q1 on A is Q2 and Q1 on B is Q1. Next, Q2. Q2 on A is Q1 and Q2 on B is Q2. Okay, so what are the final states? Q1 and Q2, both are final states. Q1 and Q2, Q1 and Q2, both are final states. What is the first one? You have to write zero equivalence. So what is zero equivalence here? In this case, zero equivalence is nothing but set of final states and non-final states. Non-final state is Q0 and final states is Q1 and Q2. It is important. All the final states will be in one group and all the non-final states will be in the other group. Now what about one equivalent? You need not do anything with Q0, leave it. Now go to Q1 and Q2 and just check them if we can separate them or not. If you look at Q1 and Q2, they are in the same state. See, Q1 and Q2, they are going to Q1 and Q2, which are in the same group in the zero equivalent, and Q1 and Q2 are going to Q1 and Q2, which are in the same state or same group in the previous equivalent. Therefore, Q1 and Q2 cannot be separated. So if there are two equivalences adjacent which are same, then actually you can stop there. Even if you go to 2 equivalent, you will get the same. Even if you go to 3 equivalent, you will get the same, which means Q0 and Q2 has to be the same state. Now the answer looks like this. If you have to draw the transition diagram, Q0 on A and then Q1, Q2. These two will be in one state. Now Q0 on A is going to Q1, which is nothing but Q1, Q2, and Q0 on B is going to this one, right? And next one is Q1 on A is going to Q2, so on A or B it will be same. See, Q1 on A is going to Q2, Q1 on A is going to Q2, and Q1 on B is going to Q1, Q1 on B is going to Q1, Q2 on A is going to Q1, Q2 on A is going to Q1, and Q2 on B is going to Q2, same, right? So this is the final state also. What is this DFA? It is nothing but DFA which accepts set of all strings containing A. Even if you look at this, once I see any number of B's and if I see a and if I reach this side, whatever I see next, everything is accepted, isn't it? So once I see a, if I come this side, whatever I see next, everything is accepted. This is how we should be doing the minimization. So this is done. Now let's try to minimize this DFA. First of all, it is a DFA, you can check it. For every state there is a transition on small a and small b, and it is, let us assume that this is input given and I have converted it to the table. Then before going further and applying the 0 equivalence, 1 equivalence, this partitioning method, let us see if all these states are reachable from Q0. From Q0, which is initial state, Q1 is reachable, right? And from Q0, Q3 is reachable and Q2 is reachable. What about Q4? From Q0, Q4 is not reachable. In fact, this entire part is not reachable from Q0, which means I could actually delete this entire part. Q4, Q5, Q6, Q7. You just check it. See, arrow is this side. So arrows are coming from this right hand side to left hand side. Nothing is going from this side to that side. Therefore, they will never be reachable from Q0, the initial state. And so I can remove Q4, Q5, Q6 and Q7. So Q4, Q6, these are removed. Now you can simply consider it as 4 states and you can minimize it. What is the initial state? Q0. What is the final state? Q3. Q3 is the final state. Okay, so apply the partitioning method. First one is 0 equivalence. Set of non-final states and final states. What are set of non-final states? Q0, Q1, Q2. And what is final state? Q3. Okay, 1 equivalent. Now let us see if Q0 and Q1 are 1 equivalent or not. How can you check it? Take Q0 and Q1 and see their transitions. Q0 and Q1 and see how they are behaving, right? Q0 and Q1 on small a are going to Q1 and Q0. Both are in same group, Q1 and Q0, and they are going to Q0 and Q2. Both are in same group. Therefore, Q0 and Q1 are 1 equivalent. Q0 and Q1 are 1 equivalent. Now, what about Q2? Now let us compare Q0 and Q2. Q0 and Q2. Q0 and Q2 are going to Q1 and Q3. Q1 and Q3, which means they are going to different groups. Therefore, Q2 is not 1 equivalent with Q0 or Q1. So this is what I get. Fine. Now again let us check 2 equivalent. How can I check 2 equivalent? Now see, these two have already been separated and they are the singleton sets in their group. Therefore, I need not check about them. They are saying that we are not equivalent to any of the states. Therefore, I need not check them again. Now let us see these two, Q0 and Q1. Q0 and Q1 on small a are going to Q0 and Q1 and both are in same group. Q0 and Q1 on small b are going to Q0 and Q2. Q0 and Q2, which means both of them, see, Q0 and Q1 on small b are going to Q0 and Q2. Q0 and Q2, which means they are going to different groups in the previous equivalence. Therefore, they are no more equivalent. Q2, Q3. So in the given question we have 4 states, and in the minimal automata also we have 4 states. So these 4 states cannot be reduced, and this is the final answer. Now let's try to minimize this DFA. Okay, first of all it is DFA because you can check it. For every state, for every symbol, here the input alphabet is 0, 1 and states are ABCDs, right? So this is a DFA. For every state and for every symbol there is a transition, and I have just written the transition table for the DFA. So before going ahead and then minimizing it, just see if all the states are reachable or not. B is reachable, right, and C is reachable, right, and D is reachable, and E is reachable. Yes, all the states are reachable. Fine. And what is the final state? Initial state is A and final state is E. So these are the final states. E is the final state. Okay, so let's write down the zero equivalence. Zero equivalence is set of non-final states and final states. Set of non-final states are A, B, C, D, and final state is E. And one equivalence is I'll see if any of these states can be written apart. Let us take A and B and C. If I see A and B, they are going to BC. BC is in one group, and D both are in different groups. Therefore, A and B have to be separated. Now let's take C and see with what should I be writing it? A and C. Let us check A and C. A and C are going to BB. Yes, they are in the same group. DE. Again DE are in different group. Therefore, A and C are not in same group. Let us compare B and C. If I see B and C on 0 are going to B and C are in same group, and E and E are in same group. Therefore, B and C are in same group. Now let us see if C and D are in same group. Let's compare C and D. Yes, if I compare C and D, now you can understand that C and D on 0 are going to B and C, they are in same group, and E and D, they are in same group. Therefore, D is in same group with C. Fine. So this is how one equivalence looks like. Now let us say two equivalent. How do I get two equivalent? I'll take one equivalent and then the transition. Now B and C. Let us compare B and see what happens. B and C on 0 are going to B and C. Yes, they are in same group. And E and D. Yes, they are in same group. E and D are in same group, which means the same state, right? So B and C are going to be in same group. And what about D? Let us compare C and D. C and D are going to B and C. B and C are in same group, and E and D. Obviously, it is just one state. Therefore, B, C, D are in same group. Fine. Now check these two. We have reached a state where the sets and the values are not changing over the equivalences. Therefore, we can stop here and say that we have three states in the final automata. So let's see how this final automata looks like. So it is nothing but they are saying that A is the initials, A is one state, B, C, D are in one state, which means they are saying that all the entire B, C, D are in one state. So it looks like this: A, B, C, D and E. We have only three states. A is one state, B, C, D are one state, and E is one state. Now small a on 0 or 1, it is going to B. Small a on 0 is going to B, which means on 0 I should take it to B, which will even contain B, C, D, right? And 1 it is going to D, so which means it is again B, C, D. See, if it is going to D, then make a transition to a state containing D. Okay, and B, so I'll take small b and discuss. And small b on 0 is going to C, which means on 0 is going to C. Small b on 0 is going to C itself, which means you have to make a transition to the state containing C. And small b on 1 is going to E. 1 is going to E. This one is complete. Again, E is going to E itself, 0, 1, right? This is the final answer. Now let us consider the finite automata with output. Till now we have seen finite automatas without output. So one is DFA and other is NFA. Now let us even consider the finite automatas where they will take an input as well as they will keep on writing the output. For example, we have two kinds of machines. One is Moore machine and other is Mealy machine. So in order to discuss about Moore machine as well as Mealy machine, we are going to see the common part of them. Both of them can be represented by Q, sigma, delta, Q naught, capital delta and lambda. Okay, this is lambda and this is capital delta. Now both of them can be characterized using these values. What does Q mean is, Q is the finite set of states. If you take an example, so both are containing some states, Q0, Q1, so on like that. So Q is finite set of states and sigma is input symbol, input alphabet. So it is simply like, we have seen before what is sigma, same in input alphabet. And delta is transition function. It is worth noting here, transition function is defined as Q cross sigma to Q. So what it means is, a transition function or the transitions in the finite automatas of Moore or Mealy are going to depend on the state, the current state Q and the input. So depending on the current state and the input, they are going to change their state. So it is same as DFA. Therefore you can even call both of them as DFAs. So both are deterministic. You should not call them as DFA, but then both are deterministic. So both Moore machine and Mealy machine both are deterministic. And Q0 is input alphabet, or in the initial state, and capital delta is output alphabet. So what is output alphabet? Output alphabet is nothing but the symbols which are supposed to be printed, or the symbols which will be outputted by these automatas is nothing but output alphabet. And capital delta is output function. What is output function is, this function will determine what will be printed as the output. So the only difference between Moore machine and Mealy machine is only the lambda. So if you look at Moore machine, in Moore machine, lambda is a function of see this, lambda is a function from Q to delta, which means for every state input is output is associated. For example, for every state this is the output 0, for this state 1 is the output. So lambda says that for every state output is associated. So in this case, especially in this diagram, for this Q0 output associated is 1 and for this Q1 output associated is 0. And if you look at Mealy machine, in Mealy machine output is associated like this. For a state, for a given input, there will be some output. For a state, for a given input, there will be some output, which means, let us say state Q0. For a state Q0, for the given input A, output is 1, which is nothing but, for state Q0, if the input is A, then output will be 1. Similarly, for a state Q0, if input is B, then output will be 0. See, for a state Q0, if input is B, output will be 0. For a state Q1, if input is B, output will be 0. For the state Q1, if input is A, output will be 1. So the only thing you have to remember is, Moore machine is going to associate a symbol or the output with the state itself, and the Mealy machine is going to associate output as a combination of the current state as well as the input. So one thing how you can remember it is, if you write Moore spelling, M-O-O-R-A, Moore spelling, then you can see these two O's, one output. First O is 1, second O is output. That is how I remembered, which means for every state we are going to have one output. I'll take an example and I'll trace out how it really works. Let us say this is the finite automata and I don't know what is it doing exactly, but then this is just an example. So this is the Moore machine. On this Moore machine, what happens if I give an input AB? Initially I'll be in state Q0. Whenever I am in state Q0, output associated is 1. Therefore 1 will get printed. Now on seeing a small a, I'll again go to state Q0 itself. Therefore again 1 will be printed, and Q0 on B is going to Q1. Q0 on B is going to Q1. Therefore, in state Q1, output associated is 0. So, on seeing input AB, this particular Murray machine has printed the output 110. On seeing input AB, this particular Murray machine has printed the output 110. So you can think of it this way: if I give a string of length n as input, then the output produced will be a string of length n plus 1. If I give a string of length n as input, then the output produced will be a string of length n plus 1. This is because even without seeing anything, Q0 is going to produce something. That is the reason. Even without seeing anything, Q0 is going to produce some output. That is why after seeing inputs, again we are going to get output, and initially we are going to get one output. Therefore, n plus 1 strings or n plus 1 outputs will be formed over a string of length n. Now let's trace the example of this one, Mealy machine. Let's take the same example in Mealy machine. In Mealy machine, if I have the example of, let us say, AB itself, initially I will be in Q0. Since output is not associated with the state, it will not print anything. Only upon seeing small a, Q0 on small a, Q0 on small a, it is going to print 1. Q0 on small a is going to print 1, and it is going to enter Q0. Now Q0 on small b is going to Q1, and it is going to print 0. Therefore, here output is associated with the inputs. So if I give n bit input, then the output will be n bit. But in case of Murray machine, if I give n bit input, output will be n plus 1 bit. In this case, if I give n bit input, then the output will be n bit. Now let us take each one and we shall solve some problems. Now let's try to construct a Murray machine. So Murray machine is nothing but a deterministic machine in which output is associated with state, which means for every state we have only one output. Now we have to construct a Murray machine that takes set of all strings over a comma b, which means it is going to take all the strings which are possible over a comma b as input. So input alphabet is nothing but sigma equal to a comma b, that is what they have given, and prints 1. So output, they have to print 1 as output for every occurrence of AB as substring, which means whenever I see AB, I have to print a 1 as output. Okay, so output, let us say capital delta should contain 0 and 1. So output is 0 and 1, input is a comma b. Now the problem is this: whenever I give any string which is containing AB, it should print 1. If I give AB and AB, it should print 2 ones. If I see AB, BB, AB, it should print 2 ones here, that's it. And I don't care how many zeros it is going to print. For every AB, it is going to print 1. It is nothing but discounting number of ABs. So in order to construct this, we have to decide about 3 things. One is, we can design the deterministic finite machine for set of all strings starting with AB. See, we have to count number of ABs. For that, if I use the problem of starting with AB, the problem here is we are actually seeing only one AB and we are not seeing all the remaining ABs. If I say containing AB, it will be again starting with anything and then containing AB, which means we will be seeing only one AB, and after that we are not going to count. But if you take ending with AB, there we are going to actually count. Using that, we can actually count all ABs. Therefore, in order to solve this problem, I am going to construct a finite automata, or let us say a DFA, which accepts set of all strings ending with AB. Okay, so if you remember how to construct set of DFA for set of all strings ending with AB, this is how it looks like. I am not going to talk about the procedure, you already know it. Let us say ending with AB, initially I will be waiting for A and then any number of A's, that is not a problem. And if I see a I'll again wait for a B. If I see a B, I'll again wait for this. So this is actually DFA, which accepts set of all strings ending with AB. right? So if I see any number of B's, I'll be waiting for an A. So even if I get any number of A's here, it is still ending with A. So if I get a at the end, it means that entire sequence, a sequence has spoiled. I have seen A, B and reached this. Let us say capital A, capital B, capital C are the states. Now I have reached C on seeing a B. If I see a at C, I have to again wait for a B. Therefore, I'll go here and wait for a B. If I see a B at C, then I have to again see a B to reach it. Therefore, whenever I reach C, I'll reach C on seeing a B. See this? I'll reach C directly on seeing a B, or AB, and again when I see one more AB, I'll reach it, or AB, and again I can go back and again I can come. So whenever I see AB, I am actually reaching the state C. Therefore, according to the problem specification, if C is made to output 1, that can solve our problem, right? So whenever I see AB, I'll be in state C and it is going to output 1. And for the remaining states, you can simply give 0 as the input, right? So let us take an example and see this. Let us say the input is small a, small b. If I am in state capital A, if I see 0, I'll go to state capital B. And sorry, if I see A, I'll go to state capital B. If I am state capital B, if I see a small b, I'll go to state capital C. Now capital A is going to print 0, capital B is going to print 0, and capital C is going to print 1. Therefore, on seeing AB, I am able to print 1. If I see AB, AB, let's see what happens. I'll be in capital A. So capital A on seeing small a is going to capital B, and capital B on seeing small b is going to capital C, and capital C on seeing small a is going to capital B, and capital B on seeing small b is going to capital C. And now the output printed is, for A it is 0, output associated is 0, for B it is 0, for C it is 1, for B it is 0, for C it is 1. So which means for every occurrence of AB, I have printed 1, which is nothing but I have counted the number of occurrences of AB in a particular string. Okay, so this is the final answer. In the previous problem, we have constructed a Moore machine which has taken set of all strings over A comma B and counted occurrences of AB. Now I wanted to count the occurrences of BAA. So sigma is A comma B, and in order to count all occurrences of BAA, I will assume that the output is 0 comma 1. You can take any output, it is just a matter of convenience. Okay, so how can I count occurrences of BAA? So in order to count the occurrence of BAA, you have to construct the DFA that accepts set of all strings ending with BAA. Whenever you have to count, always remember ending will help us because it will keep track of all BAAs. Okay, so this is the DFA which accepts set of all strings ending with BAA. Okay, I need not have a final state. Now this state will wait for a B, any number of A's, it will accept it, and now any number of B's, it is going to be BAA only, and if I see a it is going to be there, and if I see a B, I have to come back and I will wait for BAA, and if I see a it is not ending with AAA, so if I see a I have to again come back and wait for BAA. Fine. So this is the what happens for B. If I see a B, I have to come back here. Okay, so this is the deterministic machine. So check it. On small a and small b it is complete, and small a and small b it is complete, and small a and small b it is complete, and small a and small b it is complete. So let us name the states. Let us say the state is capital A, state is capital B, capital C, and capital D. Now if you look at all the states, how do we reach capital D? We reach capital D whenever we see BAA. Either we see BAA here, and if you see one more BAA, again we reach, or let us say you have seen BAA and again BAA. So whatever way we see BAA, whenever we see it, we are going to end up at D. So it is nothing but a deterministic finite automata for set of all strings ending with BAA. Now they wanted to count all the occurrences of BAA. So whenever a BAA occurs, I am going to print 1. So I am going to associate output of 1 with state D and output of 0 with states A, B and C. So A, B and C are just simply going to output 0 and D is going to output B. So let us take an example and work it out. Let us say B, A, A. I will be initially in state A, and on seeing small b, I will be going to state B, and on seeing small a, I will be going to state C, and on seeing small a, I will be going to state D. Now what is the output? 0, 0, 0, 1. Therefore on seeing BAA, I will be printing 1. Take one more example. Let us say I am seeing BAA, again BAA. I will start from A on small b is going to B, B on small a is going to C, C on small a is going to D, and again D on small b is going to D, on small b is going to B, and B on small a is going to C, and C on small a is going to D. Now just check the output. 0, 0, 0, 1, 0, 0, 1, which means if I see 2 BAAs, 2 ones will be printed, right? So if I have to count something ending with, or if I have to count some substring, always remember we have to construct a DFA which accepts set of all strings ending with that substring, and then the final state, in the final state you just output 1. So this is the solution for this question. Now let us say we have to construct a Moore machine which takes set of all strings over 0, 1, which means sigma equal to 0, 1, and produces capital A, which means delta is going to output has to be capital A. If capital A as output, if input is ending with 1, 0, which means if the input ends with 1, 0, I should produce capital A, or produces capital B as input ends with, as output if input ends with 1, 1. If the input is ending with 1, 1, I have to produce capital B, otherwise it produces C, which means I have to identify between 3 cases, whether the input is ending with 1, 0 or the input is ending with 1, 1. Fine. So how we can do it is, we have to directly draw a DFA where a string is going to end with 1, 0 or 1, 1. So DFA for strings which have to be, we are going to accept set of all strings which are going to end with 1, 0 or 1, 1. So initially I am going to see 1. See, I am not going to explain the method of how to construct the DFA, that we have already discussed in the previous question. So I am directly going to draw the DFA. So if it is going to end with 1, 1, I will be in this state. If it is going to end with 1, 0, I will be in this state. Okay. So now let us fill the finite automata. So let us assume that the states are x, y, z, because ABCs have already been taken for delta. Let us say x, y, z and w, right? So if the input is going to end with 1, 1, I should print B. So in Z I am going to print output as B, and if the input is going to end with 1, 0, I have to print A. Therefore here I am going to print A, right? So let's finish the deterministic finite machine. In capital X, if I see any number of zeros, I should just wait for 1, and this is complete. And capital Y can see 0 or 1, that is complete. Now if I am in state this one W, how did I raise this W? After seeing 1, 0. If I see one more 1, I should either wait for a 0 or 1. So if I see one more 1, I'll either wait for a 0 or 1. Now if I am in 0, 0, if I am state W, which means I have seen 1, 0, if I see a 0, the entire sequence is spoiled, and again I have to wait for 1, 0 or 1, 1, which means if I see a 0, I'll come back and again I'll wait for 1 0 or 1 1. So this one is complete. Now in state Z, how did I reach Z? I have reached Z by seeing 1 1. If I see one more 1 or any number of ones, it is still ending with 1 1. Therefore any number of ones is still ending with 1 1. Now again I have reached Z on seeing 1 1, on seeing 1 1. If I see a 0, it is nothing but ending with 1 0. If I see a 0, I'll come here. Why? Because it is ending with 1 0, right? So this is it. If I am in cap W, the output has to be A. If I am in Z, the output has to be B. Otherwise the output has to be C. So in the remaining states, output has to be C. Now you can just give me an example and we shall trace it out. Let us say I have to trace out the example 1 1. The input is 1 1 1, which is ending with 1 1. Therefore the output has to be B. So I'll start with X. Initial state is X, and on seeing 1 I'll go to Y, and on seeing 1 in Y I'll go to Z, and on seeing 1 in Z I'll still go to Z only. So the outputs are going to be C, C, B, B. So what we need not care about all these things, we are going to care about the last output, which means if the input is going to end with 1 1, definitely we are going to see B in the ending. Let us say 1 1 0 is the input, then initially I will be in state X. On seeing a 1 I will go to state Y, and on seeing a 0 in Y I will go to state W, and on seeing a 0 in W I'll be going to one second. So let us say input is 1 1 0, on X on seeing 1 is going to Y, Y on seeing 1 is going to Z, Z on seeing 0 is going to W. Now look at the outputs. What is the output associated with X? C, Y C, Z B, and W A. Therefore final output is A. This is what matters, not all this, right? So if the input is going to end with 1 0, we are going to see A. If the input is going to end with 1 1, we are going to see B. Don't care about the other outputs. Okay, so this is the solution for the given problem. Let us say we have to construct a Moore machine that accepts set of, or that takes set of all binary numbers, which means sigma equal to 0 comma 1 and produces residue modulo 3. What does it mean is, if I take a binary number and if I divide with 3, whatever is the remainder, that should be printed, which means the output has to be remainders when any number is divided by 3. So what are the possible remainders? 0 1 2. So input is going to be binary numbers and output is going to be reminders. So we have seen this problem long back, where we have constructed DFA which accepts set of all strings which are divisible by 3. We can use the same one. So what is the shortcut for that? Whenever I say a number has to be divisible by 3, the number of states are 3. Let us say Q0, Q1 and Q2. Q0 corresponds to the state where the remainder is 0, Q1 corresponds to the state where remainder is 1, Q2 corresponds to the state where remainder is 2. Okay, and I have told you how to draw this. The shortcut is this: directly draw the state transition table, right, and fill it like this: Q0, Q1, Q2, Q0, Q1, Q2, done. So this is the DFA which accepts set of all strings which are divisible by 3 in case if you have Q0 as the final state. Now I don't want that, I don't want a DFA, I want a Moore machine which should actually print the output, which is nothing but the remainder. If I am in state 0, then the remainder has to be 0. If I am state Q1, then the remainder has to be 1. If I am state Q2, remainder has to be 2. So the Moore machine can be constructed by adding the delta function. So if I am in state Q0, the output has to be 0. If I am state Q1, the output has to be 1. If I am state Q2, the output has to be 2. This is the state transition diagram for the Murray machine, or you can even draw the state transition diagram, not the table, right? So instead of drawing the state transition table, how does the state transition diagram look like is, you will be in Q0, you will be printing 0. If you are in Q1, you will be printing 1. If you are in Q2, you will be printing 2. Reminders are that, right? And now Q0 on 0 is going to 0 itself, and Q0 on 1 is going to Q1, and Q1 on 0 is going to Q2, and Q1 on 1 is going to Q0, and Q2 on 1 is going to Q2 on 0 is going to Q1, and Q2 on 1 is remaining in Q2 itself. So this is the state transition diagram for the same question, and this is the state transition table. For such a question, whenever it is divisible by 3 or residuo modulo 3, it is easier to go with this particular kind of state transition table. The reason is, you can even extend the question to even other levels. Let us say I want to extend the question like this: construct a Murray machine that takes all, instead of binary numbers, let us say I want to take all base 4 numbers, and that produces, instead of saying residuo modulo 3, I can say residuo modulo 5, right? So what should be the input? Input is all base 4 numbers. What are all base 4 numbers? 0, 1, 2, 3. And the output is residuo modulo 5. So what are the reminders when I divide any number with 5? 0, 1, 2, 3, 4. These are the reminders when I divide any number with 5. So you can follow the ordinary method. What is it? When I divide any 5, the reminders, any number with 5, the reminders are 0, 1, 2, 3 and 4. These are the reminders when I divide any number with 5. Let us say Q0 is the initial state, and what are the inputs? Inputs are 0, 1, 2, 3. And now you fill out the delta function like this. So what is the delta function? Directly Q0, Q1, Q2, Q3, Q4, again Q0, Q1, Q2, Q3, Q4, Q0, Q1, Q2, Q3, Q4, Q0, Q1, Q2, Q3, Q4. So this is same, the delta function is same, even though this is nothing but the transition table for a DFA which accepts set of all base 4 numbers which are divisible by, let us say, 5, or which is congruent to 1 mod 5 or 2 mod 5, 3 mod 5, 4 mod 5, anything. Only change is you have to add the delta function. What is the output? If I am in state Q0, the output has to be 0. If I am state Q1, the output has to be 1. Why? Because that is a reminder. If I am in state Q2, output has to be 2. Q3 output has to be 3. Q4 output has to be 4. You can take any example and you can trace it out, but I am leaving that as an exercise for you. Check it out. Okay, this is where I am going to stop. Till now we have seen Murray machines. Now let us see a Mealy machine. Now the question is, construct a Mealy machine. Mealy machine is nothing but for every state, for every input there will be an output. It is not just output is not just associated with the state. For every state, for every input there will be an output. So the question is, construct a Mealy machine that accepts all binary strings, which means sigma input equal to 0, 1, and now we should produce 2's complement of the binary number. So therefore output is also a binary number which should be 2's complement of the input. If I say input is some number, output has to be 2's complement of that. Assume that this string is read from LSB to MSB and end carry is discarded. Okay, so before actually doing this problem, let us try to do some simple problem where where I'll take a binary number as input and I'll produce ones complement as output. Ones complement as output. So that will be simple. What is ones complement? Let us say if I have 0, 1, 1. What is ones complement? 0, 1, 0, 0. Wherever you see 1, convert it to 0. Wherever you see 0, you convert it to 1. So that must be very simple. I'll be in initial state. If I see a 0, I'm going to convert it as 1. If I see a 1, I'm going to convert it as 0, and just one state is required, nothing else. So if you have to trace out and see how this one is working, I'm talking about ones complement, not twos complement. I didn't reach this problem yet. Okay, so if the input is 0, let us say 1, 0, 1, 1, then I'm going to start in Q0. On 1 I'll be in Q0. Q0 on 1 is going to print 0, and again on 0 I'll be in Q0 only. Q0 on 0 is going to print 1. Again on seeing 1 I'll be in Q0 itself. Q0 on 1 is going to produce 0. Again on 1 I'm going to in Q0 only, and Q0 on 1 is going to produce 0. So that is how we got ones complement, right? So ones complement is easy, simple. So whenever you see a 0, you are going to print 1, and whenever you see a 1, you are going to print 0. But twos complement is not that easy, and moreover twos complement has to be, let us talk about twos complement first. Let us say I have a number 1 0 0 1 1 0 0. Okay, I want to find out the twos complement. How to find the twos complement of this? First you find ones complement, which is 0 0 1 1, and then you add a 1. Then what do I get? 0 1 0 0. This is the twos complement. So let's take one more example. 1 1 1 0 1 1 0 0. So I want to convert this to a twos complement. First convert it to ones complement. Ones complement is going to be 0 0 0 1 0 0 1 1. And now in order to convert it to twos complement, add a 1. So what do I get? 0 0 0 1 0 1 0 0. Simply adding 1, right? 1 plus 1 is 0, and again you get a carry here. 1 plus 1 is 0, so again you will get this one and carry here. So that is how you got. Now you just check these two numbers. This is the original binary number, and this is the twos complement of it. If you look at this, if I am reading from LSB to MSB, if I have zeros in the beginning or zeros from the LSB side, LSB is this least significant bit and most significant bit. If I am reading from LSB to MSB, whenever I have zeros, I am leaving them as zeros, and whenever I see first one, I am leaving it as 1, and whatever is there after that first one, it is going to be complemented. Check this. All the zeros are left as zeros, and whenever I see first one, that is left as 1, and after that whatever I see, I am complementing this. You will understand better in this example. See, whatever are zeros, that will be left as zeros. Initial two zeros are left as zeros, and then once I see first one, that will be left as 1 itself, and after that whatever number is there, that will be ones complemented, and after that whatever number is there, that will be ones complemented, which means 0 1 1 1 1. You can take one more example. Let us say 1 1 1 0 0. What is the ones complement of it? 0 0 0 1 1. What is the twos complement of it? Add a 1 to it, then it is going to be 1 0 1 0 1 0 0. Whatever is the least significant zeros, you are going to write it as it is, and the first one you are going to write it as it is, and after that whatever is remaining, we are going to take ones complement of that. So by this you should understand one logic. If I am going to start from LSB, whatever are zeros there, I am going to leave them as zeros, and after seeing the first one from the LSB, I will leave it as 1, and after that whatever I see, I am going to apply ones complement. Again see this, whatever are zeros, I am going to leave it as zeros, and whenever I see the first one, that first one will be left as it is, and whatever is the remaining string, that will be like this. What if there are no zeros at all? Then it is going to start with 1 itself, right? What if there are no zeros at all? Let us say, you can even talk about this example, 1 0 1 1, there are no zeros at all. Let's see how it works. So it is going to be 0 1 0 0 is the 1's complement, and 2's complement is 1 0 1 0. So what happened, whenever I see the first one, that first one is going to remain as it is, and after that everything is going to be complemented, right? So we don't care what happens after the first one. So if there are zeros, they will be left as it is, and the first one will be left as it is, and whatever is remaining on the left of it, that will be once complemented. Okay, so now let's construct the Mealy machine for this. The Mealy machine will actually look like this. I'm assuming that I'm reading from LSB. So initially I'll be in state Q0. In this state I'll be seeing zeros and I'll be leaving them as zeros. Whenever I see a 1, I'll remember that I have seen a 1 and I'll print 1 and I'll go to next state, and this state will actually complement everything, which means if I get a 0, 0 is printed, 1 is printed, and if I get a 1, 0 is printed, right? So if I have to explain this, I'll take an example. Let us say the example is 1 0 1 1, or maybe I'll take another example, 1 1 0 0. What is 1's complement of it? 1's complement is 0 0 1 1, and what is 2's complement of it? 2's complement is 1 0 1 0 0, right? So I'll take this number 1100 and I'll give to this automata Mealy machine, and I'll get this output. See this, 1100 Q0 on 1 is going to Q1, and now Q0 on 1 is going to Q1 and is going to produce 1, right? And we are supposed to read from the ending, right? We are supposed to read from the LSB, which means I should write it as 0011. Okay, now Q0 on 0 is going to produce 0 itself and stay in Q0 only. Again Q0 on 0 is going to stay in Q0 itself and going to output 0 only, and Q0 on 1 is going to produce 1 and is going to go to state Q1, and Q1 on 1 is going to Q1 itself and is going to produce 0. So what is the answer? You have to count it in the reverse order, which means the 2's complement is 0010 0010. Got it? So this is how it is built. Now let us say this is the question given. What is the output produced by the following state machine? This is some machine. If you look at this machine closely, you can understand that it is a Mealy machine, and in Mealy machine they are given some options A, B, C, D. We have to choose which one is right. So if you look at this question, the first option is saying that if I give input 1 1, it is going to give output as 0 1. So obviously it is false. Why? Because for every one symbol it is going to print two symbols, so it cannot give two symbols, and this is wrong and this is wrong. And let us see if this is right. Sum of present and previous bits, right? So in order to check this, let us take an example and trace it out on this. So for such questions, whenever they give you any diagram which is a finite automata, and if they ask you which of the following is right, always take an example and trace it out, then you'll understand better. Let us say I have to trace it out, maybe 1 1 0 1. Okay, so I'll start in state Q0. On seeing a 1, in Q0 on seeing a 1, I'll print 0 1. I'll print 0 1 and I'll go to state Q1. Now I am in state Q1. In Q1 on seeing a 1, I'm going to print 1 0 and I'll be going to state Q2, and on Q2 upon seeing a 0, I'm going to print 0 1 and I'm going to state Q0. and in Q naught on seeing a 1, Q naught on seeing a 1, I'm going to print, Q naught on seeing a 1, I'm going to Q1 and I'm going to print 0 1. Okay, now just see if this is right or wrong. Initially there is only 1, so there is no previous bit at all. Let us assume that previous bit is 0. In that case, 1 plus previous bit 0 is going to give us a sum of 1. Yes, it is true. Now you are here. At this point, you have seen the present bit is 1 and the previous bit is 1. Therefore, the sum is 1 0. Yes, 1 0 is right. And let us say you are here and the present bit is 0 and the previous bit is 1, and therefore the sum has to be 0 1. Sum is 0 1, which is nothing but 1. And let us say you are here, the present bit is 1 and previous bit is 0, therefore the sum has to be 0 1, right? So we have seen that it is actually producing the correct output, which means it is nothing but a adder which adds the present bit and the previous bit. C is the correct option. Okay, this is the problem. Till now we have seen many problems about Mealy machine and Moore machine. Now the question you should ask me is, which one is more powerful? So if I have to say that one is powerful than the other, one should be able to solve some problems which the other will not be able to solve. Let us say we have seen two kinds of finite automata with inputs. See, finite automata with inputs, with outputs, we have seen two types. One is Moore machine and other is Mealy machine, right? And we have constructed for many problems both of them. Now the obvious question is, which one is powerful than the other? If I have to say that Moore is powerful than the Mealy, then Moore should be able to solve some problems which Mealy will not be able to solve. Or if I have to say that Mealy is powerful than Moore, then it should be able to solve some problems which this machine will not be able to solve. But both are actually equivalent in power. If I have to show that both are equivalent on power, then I'll take a Moore machine, if I can convert it to Mealy, and if I can take any Mealy machine and if I can convert it to Moore, then we can say that both are equivalent. So in this question, let's take an example of Moore machine and convert it to Mealy. So let us say I want to count number of A's using a Moore machine. So, or I want to print out number of A's mod 3. Then the Moore machine is going to look like this. We have three states. We'll have three states: Q naught, Q naught, Q1 and Q2. So let us assume that we are counting only A's. So on A's we are counting, and on B's we will not count. So on B's we will not count. Okay. So what is the remainder in Q naught? Remainder in Q naught is 0. See, this is nothing but the some DFA which accepts set of all strings in which number of A's is divisible by 3 or congruent 1 mod 3 or congruent 2 mod 3. So, and this is the Moore machine which will print out the remainder of number of A's when divided by 3. So let us say this is 1 and this is 2. Fine. So this is the Moore machine, some Moore machine. Don't worry about what it is doing. This is some Moore machine. Now I want to convert it to Mealy machine. So what is the main difference between Moore and Mealy? In Mealy machine, the output has to be associated with the transitions rather than the states. In Moore machine, output is associated with states. So I have to move the output onto the transitions. So understand this. I'm going to explain this in two ways. One is by transition diagram, other is by transition table. First, let us try to understand it in terms of transition diagram, state transition diagram. It will be very easy. Just see this. Now see this transition. This transition is going from 0, Q0, and is going to Q0. So wherever it is leading to, just go to that state and see the output associated. Since the output associated is 0, I am going to write it on the transition. Since this edge is going to Q0 and the transition and the output associated with Q0 is 0, therefore I am going to write it as Q0. Now check this edge. This edge is going to Q1 and the output associated with Q1 is 1, therefore I will write 1. Now see this, edge is going to Q1 and the output associated with Q1 is 1, therefore I am going to write Q1. Now see this is going to Q2 and the output associated with Q2 is 2, therefore I am going to write it as 2. And this is going to Q2, output associated with 2. And this is coming to Q0 and output associated is 0. So this is the Mealy machine. So you can simply remove this, and this is the Mealy machine. Now the output is associated with transitions rather than states. So how did I convert it? I have first finished the diagram for Murray machine, and then I have taken each transition, and if a transition is going to some state, I'll take the output associated with that state and I'm associating with the transition. Now let us take the state transition table for the same Murray machine. Now Murray machine state transition table is like this. Q0 is the start state, Q1 and Q2, and inputs are A and B. So Q0 on A is going to Q1 and Q0 on B is going to Q0 itself, and Q1 on B, A is going to Q2 and B is going to Q1 itself, and it is going to Q0 and it is going to Q2 itself. So this is the state transition diagram for state transition table for Murray machine. Now what is the output? Output associated with Q0 is 0, output associated with Q1 is 1, output associated with Q2 is 2. So in order to convert this table into Mealy table, first construct the table and then see this. What is the state it is going to? It is going to the state Q1. Now go to Q1 and see what is the output associated. Therefore we get 1, which means Q0 on small a will go to Q1 and output as 1. Okay. Now again see this. This is going to Q0. What is the output associated with Q0? It is nothing but 0. Therefore you write 0, which means Q0 on B will go to Q0 and output 0. Q0 on B will go to Q0 and output 0. Now look at this. It is going to Q2, therefore go to state Q2 and whatever is the output associated with Q2, write it there. Which means Q1 on A is going to Q2 and outputting 2. Q1 on A is going to Q2 and outputting 2. Now check this one. Q1, so go to state Q1 and what is the input? Output associated 1, therefore write it as 1. Which means Q1 on B is going to Q1 and output 1. Which means Q1 on B is going to Q1 and output is 1. Next one, check this. What about Q0? Q0 output associated with Q0 is 0. Therefore Q2 on A is going to Q0 and output is 0. Q2 on A is going to Q0 and output is 0. Now see this, Q2. Fine. So Q2, what is the output associated with Q2? It is 2. Therefore I am writing it as 2. Which means Q2 on B is going to Q2 and the output is 0. Output is 2. Q2 on B is going to Q2 and the output is 2. So how did I construct this? Initially I have constructed the state transition table for Murray machine, given Murray machine, and then in the transitions, in the delta function, this is obviously delta function, right? In the delta function I am associating the output whatever is associated with this state. If Q1 is associated with Q1, Q1 is associated with 1, therefore I am going to take 1 and I am going to write it here. You can remove this. So this is the final Mealy machine. So we shall even see more examples. Fine. Now let's try to convert this Murray machine to Mealy machine. This is a Murray machine because output is associated with the states. Output is associated with this state. with this state. Okay, so what is the method? So method is always whenever a transition is going into some state, whatever is the output associated with that state, take it and write it there. Since the transition is going here and the output is 0, therefore I am going to write it as 0. And since the transition is going here and the output associated with this state is 0, I am going to write it as 0. And since the transition is like this, I am going to write it as 0. Transition is 1, I am going to write it as 1. Transition is 0, I am going to write it as 0. Transition is going here and the output is 0, therefore this is the Mealy machine. And if you have to see how to convert a transition table for the same diagram, the transition table of the Murray machine to Mealy machine, then you can even look at it this way. Let us say A, B, C are the states and small a and small b are the inputs. Capital A on small a is going to B. Capital A on small b is going to A itself, and capital B on small a is going to B itself, and capital B on small b is going to C. Capital C on small a is going to capital B, and capital C on small b is going to capital A. And what are the outputs associated with the states? This is the delta function and this is the output function. So output associated is with A 0, with B 0, C 1. So what is this Murray machine? Did you find it out? It is nothing but it is counting the all occurrences of AB. It is a DFA for ending with AB, and also it is counting all occurrences of AB. So this is this transition state table. Now let's convert this transition state table of the given Murray machine to Mealy machine. So how to convert it is, go to every cell here B, and what is the output associated with B? It is 0. Therefore you associate it as 0, which means capital A on small a will go to capital B and output 0. Capital A on small a will go to capital B and output 0. See, I am not associating output with the state. No, I am associating output with the transition. See, these are the states and these are the transitions, right? So I am associating output with the transition. So if you look at this diagram, output is associated with the transition. It is, don't say that I am associating the output with the state. No, if I associate output with the state, that is Murray machine, right? Now here it is going to capital A. What is output associated with capital A? 0. Therefore I am going to write it like this. Now what is the state output associated with B? It is 0. Therefore I am writing it as 0. What is the output associated with C? It is 1. Therefore I am writing it as 1. With B it is 0. Therefore 0. With A it is 0. Therefore it is 0. Got it? So therefore this is the Mealy machine for the given Murray machine, and the Murray machine is nothing but counting the number of occurrences of ABs. So you can delete these outputs, and these are the outputs now associated with the transition, and even remember the outputs here. So if the initial machine is counting number of ABs, now the final machine, the Mealy machine should also count number of ABs. Let's take an example, A, B, and trace it out. Capital A on small a is going to capital B, and what is the output? 0. And capital B on small b is going to capital C. Capital B on small b is going to capital C, and what is the output? It is 1. So if we check this, output is 0, 1, which is nothing but I got 1 corresponding to an AB. So it has counted AB. You can even take AB, AB. Capital A on small a, capital A on small a is going to capital B, and what is the output? It is 0. And capital B on small b is going to capital C, and what is the output? 1. And capital C on small a is going to capital B, and what is the output? 0. And capital B on small b is going to capital C. What is the output? 1. So I got 2 1s corresponding to 2 ABs. Got it? So this is the answer. Let's now try to convert this Mealy machine to Murray machine. Is this Mealy machine? Yes. See this, output is not associated with the states, output is associated with the transitions. So let's take this Mealy machine and convert it to Murray machine. So how can I do it is, Just follow this method. This method must be difficult in the beginning, but then once you practice with 2-3 examples, it will be very easy. So always try to follow this method. I am not going to discuss the actual method in the textbooks. See this? Now you have to start with the initial state Q1. Okay, always start with the initial state Q1 and just see where what is the transition on 0. Q1 on 0 is going to Q2 and the output is Z1. Q1 on 0 is going to Q2 and the output is Z1. Therefore, on 0, I'll go to Q2 and the output has to be Z1, but since the output is on the transition, I'll move it on to the state. From the transition, I'll move it on to the state. Previously, from the state, we have moved it on to the transition in conversion of Murray machine to Mealy machine. Now, a Mealy machine can be converted to Murray machine by moving the output from the transition onto the state. Therefore, I am going to move it from like this. Check this. I have just moved the transition output from the transition to the state. Okay, but the problem is we may not be able to use the same method. Okay, let's see on the go. Next one, Q1 on 1. Q1 on 1 is going to Q3. Q1 on 1 is going to Q3 and the output is Z1. Therefore, I am going to move it to Z1. So this is a new state where Z1 is associated with Q3. Okay, understood till here? Now Q1 is complete. Why? Because you have shown the transition on 0 and 1. This is complete. You can either take Q3 or you can take Q2. Let's take Q3. Now see this, Q3 on 0 is going to Q2 and the output has to be Z1. See, Q3 on 0 is going to Q2 and the output has to be Z1. Therefore, Q3 on 0 is going to Q2 and the output has to be Z1. Now Q3 on 1. Q3 on 1 is going to, this is important, see this, Q3 on 1 is going to Q3 and the output is Z2. So if I write like this, Q3 on 1 itself, if I just write like this, Q3 on 1 is going to Q3 itself, this state, but the output is Z1 here, but output I needed is Z2. Therefore, I need one more state which will contain the output of Z2. I need one more Q3 which will contain output of Z2. So I am going to create one more state. On 1 I am going to create Q3 and the output is going to be Z2. This is important. See this? So even though there was only one state before, I have increased one more state for each output possible. In the conversion of Murray machine to Mealy machine, the number of states were same. But when I was converting Mealy machine to Murray machine, the number of states may increase, right? They may increase, and the number of states will increase like this. If in the initial Mealy machine, if there are n number of states and m number of outputs, if there are n number of states and m number of outputs in the Mealy machine, then in the Murray machine it may contain m into n number of states. If in the given Mealy machine we have n number of states and m number of outputs, then in the output of that, which is nothing but the Murray machine, I might have m into n number of states. So remember that the reason is, whenever I want to output Z1, yes, this state is sufficient, but then if I have to go to Q3 and output Z2, I cannot write Z2 here, because this output Z1 will get vanished. Therefore I have to create one more state which will act as Q3 itself, but the output associated with it is Z1. Okay, now you have shown what happens on 0 and 1 for this state. So this state is complete. Now you can either take Q2 or Q1, Q3. Let's take Q3. Again the same one. See, even if you are considering the Q3 again, take the same Q3, basic Q3 in the Mealy machine. Now Q3 on 0 is going to Q2 and output is Z1. Q3 on 0 is going to Q2 and the output is Z1. Now Q3 on 1. Q3 on 1 is going to Q3 itself and the output is Z2. So Q3 on 1 has to go to Q3 itself. This Q3 or this Q3? That depends on the output. The output is Z2. Therefore, this Q3 on 1 is going to be in the same state. Got it? Fine. So this one, you have shown what happens on 0 and what happens on 1, therefore it is complete. What about this one? We didn't show what happens on 0 and 1. What happens on 0 for Q2? See this, Q2 on 0 has to go to Q2 itself and the output has to be Z2. Q2 on 0 has to go to Q2 itself, but then the output has to be Z2, but the output here is Z1. Therefore I am not going to use the same state. I'll create one more state. Q2 on 0 will go to Q2 itself and the output has to be Z2. It is important. Okay, so one more state is created. Fine. Now what about Q2 on 1? Q2 on 1 is going to Q3 and the output is Z1. Q2 on 1 is going to Q3 and the output is Z1. Q2 on 1 is going to Q3 and the output is Z1. Okay, now this one is complete. What about this one? That is also Q2. So go to the basic Q2 and decide about it. Q2 on 0 is going to Q2 and output has to be Z2. Therefore this is the state. Q2 on 0 is going to Q2 itself and the output is going to be Z2. Okay, and Q2 on 1. Q2 on 1 is going to Q3 and the output is Z1. Therefore Q2 on 1 is going to Q3 and the output is going to be Z1. This is the start state. So this is how a Mealy machine can be converted to Moore machine. So in the Mealy machine, initially all the states are not having the inputs and only transitions are having the inputs, but in the Moore machine all the states have got the outputs associated with them. Now what about the initial state? It didn't get any output, right? The reason why it didn't get any output is there is no incoming edge for Q1 which is showing any output. If there would have been something like this and if there would have been some output like this, then I would have created something like Q1 comma Z1. But since we don't have any incoming edge, so we have left it like this. So in order to complete the question, you can either write Z1 or Z2, that doesn't matter. You can take any output associated with this initial state. That is not going to be a problem. So this is the conversion of given Mealy machine to Moore machine. If you practice more, it will be easy. Okay. Now let's consider this problem where this is the Mealy machine given and now I have to convert it to the Moore machine. So if this is the Mealy machine given, always start with the initial state capital A. And interestingly, in this we have an incoming edge on which we have an output, right? So what does capital A do on 0? Capital A on 0 is going to capital A and it is going to output 0. Therefore I am going to associate 0 with A, and capital A on 0 is going to capital A and is going to output 0. So it is okay. See, you can even write this as capital A comma 1 and you can create one more state as capital A comma 0, and on 0 you can give a transition. That is not a problem at all, right? But then this is simple, you can go with it. Fine. Next thing is capital A on 1 is going to capital B and the output is 1. Therefore I am moving the output here. So I created a new state capital B comma 1. So capital B is the state and output associated is 1. Fine. So this one is complete. Capital A comma 0 state is complete because I have shown what happens on 0 and 1. Now on capital B we have to show what happens on 0 and 1. See this, capital B on 0, capital B on 0 is going to capital B itself and the output is 1. Therefore capital B on 0 is going to capital B itself and the output is 1. Now capital B on 1, capital B on 1 is going to capital B itself, but the output is 0. Therefore capital B on 1 is going to capital B itself. Capital B on 1 is going to capital B itself, but the output has to be 0. Therefore one more new state is formed. This state is complete because you have shown what happens on 0 and what happens on 1. But this state is not complete because you didn't show the transition set. What happens for capital B on 0? Capital B on 0 is going to capital B and the output has to be 1, which means capital B on 0 is going to capital B and the output is going to be 1. So that is how we got it as 1 here. Okay. And what about 0? What about 1? Capital B on 1 is going to capital B itself and the output has to be 0. Capital B on 1 is going to capital B itself and the output is 0, and this one is also complete, right? So what is this problem? This problem is nothing but we are going to read a string from the RHS and we are going to print the 2's complement as output. We are going to start from the RHS or least significant bit and we are going to print 2's complement. The main difference between Mealy machine and Muri machine is in Mealy machine, if I have n inputs, which means if I give 0, 0, 1, 1, then I'll get n outputs, each one for each. Let us say, the answer could be 1, 1, 1, 1, 1, 0. Let us say 1. This could be the answer. If there are 4 bits, I get 4 bits as output in case of Mealy machine. But the problem with Muri machine is if there are 4 bits, if I give 0, 0, 1, 1, I might get 5 outputs. That is the problem. Therefore, you cannot exactly say that this is exactly equivalent, but then it can be mimicked. What my intention is, it can give us some part of answer. Therefore both are equivalent, but only problem is Muri machine is going to generate one more output compared to the Mealy machine. One point worth noting is when we are constructing or converting Muri machine to Mealy machine, number of states doesn't change. Number of states didn't change when we are converting Muri machine to Mealy machine. But when I am converting Mealy machine to Muri machine, number of states increased. Okay, and how much it increased? If initial Mealy machine contains capital N number of states and if the Mealy machine is outputting capital M number of outputs, then the final Muri machine may contain capital N into M number of states. So in the worst case, I might go up to capital N into M. In the worst case, I might go up to 4 states here because 2 states are there. In the Mealy machine there are 2 states and the outputs are 2. Therefore I might go up to 4, but in this case luckily we got only 3, right? So in any case we are going to go up to N into M states in the final Muri machine, right? This is the example. Till now we have seen DFA, NFA and finite automata with output, which are Muri machine and Mealy machines. And now let us see a special kind of finite automata, in fact is NFA. We are going to see special kind of NFA called epsilon NFA. Okay, so the word is epsilon. Epsilon means empty string. So epsilon NFA is different from ordinary NFA in the sense that if you look at any transition, that may even contain epsilon. So this is an example of epsilon NFA. So this is actually looking like a DFA or NFA, and only difference is in DFA or NFA we don't have epsilon moves, right? So in order to define this epsilon NFA, we can directly define it this way. Let us say Q, sigma, delta, Q naught and capital F. Q is set of states which we already know, and sigma is input which we already know, and delta is bit different here. Q naught is initial state and capital F is set of final states. So delta, if you remember in NFA, delta is nothing but Q cross sigma, which means if I am in some state, if I see some input, then I was going to 2 per Q, power set of Q, which means if I am in some state and if I see some input, I'll go to a power set of, I'll go to a subset of all states. Only difference between epsilon NFA and NFA is here I even have epsilon, which means on a particular state, on seeing some symbol I can go to some state, or on a particular state without seeing anything a transition is possible. See this? On A, without seeing anything, even we are going to transit some state, right? So it is also called as epsilon closure. So I'll talk about a property called epsilon closure. Now let us say epsilon closure of capital A. So epsilon closure of any state is nothing but what are all the states which you can reach only on seeing epsilon from A. Epsilon closure of A is nothing but what are all the states which you can reach from capital A only on seeing epsilon. In order to find it out, see this, always I can reach A on seeing epsilon. A can reach A on seeing epsilon. It is always there. So whatever is there in the epsilon closure, we are going to get that as the output. Therefore A can be reached, okay, and A can reach B on seeing an epsilon. Therefore B is reachable only on epsilons from A. Therefore epsilon closure of A is going to contain B, as well as B can reach D on seeing epsilon. Therefore epsilon closure of A is even going to contain ABD. This is epsilon closure. Fine. So now the question is, how can I convert epsilon NFA to NFA? Or you can even ask me a more natural question. We have seen one is DFA, other is NFA, and now we are seeing epsilon NFA. Now your question is, which one is powerful? We have already seen that DFA and NFA are equivalent in power. Why? Every DFA is nothing but NFA, therefore I can convert every DFA to NFA, and then I have even shown you a method using which NFA can be converted to DFA, right? Now in order to show that this one NFA and epsilon NFA are equivalent, see, by this definition, if you remove epsilon, it is nothing but NFA, right? Therefore you can say every epsilon NFA is NFA. So conversion from NFA to epsilon NFA is trivial. Why? Every NFA is epsilon NFA. Now if you can convert epsilon NFA to NFA, then we can say that these two are equivalent, and by extension all of them are equivalent. So now I want to take epsilon NFA and convert it to NFA. Let's see the method. Now I want to take epsilon NFA and convert it to NFA. Fine. So I'll go with the state transition table. State transition table is going to start with A. Now I'm not having epsilon moves, so I'll be writing only about 0 and 1. So first of all, in order to fill this particular entry, it is nothing but what does A, capital A on 0, where does it go? So you have to decide about capital A on 0 in the NFA. So in order to convert this DFA to NFA, I'll use this method. See this? Now I'll take state A. From state A, I have to see what happens on 0. So instead of seeing what happens on 0 directly, I'll see what is the epsilon closure of A, which means what are all the states that are reachable from A only on seeing epsilon, and then 0 and then epsilon. I'll write like this. It is nothing but, in order to find out this entry capital A on 0 in NFA, I have to find out capital A on epsilon closure, again apply 0 and again apply epsilon closure. Even you can think of it this way. So what has exactly happened is, I'm going to find out epsilon closure of A, and then whatever I get in epsilon closure of A, I'm going to find out what are their transitions on 0, and whatever is the result, I'm going to again find out epsilon closure. This is the procedure. You have to apply epsilon closure on A, and then you have to apply on 0, and then again you have to apply epsilon closure on the final result. Instead of writing like this and then expanding, I'll just use this shortcut. So what is that I'm going to do is, capital A, epsilon closure. What are all the states that are possible for A on epsilon? Only epsilons. One is A, other is B, and other is D. These are all the states where A can reach only seeing epsilons. On seeing one epsilon A, on seeing one epsilon B, on seeing two epsilons D. I should not even count them as 0 epsilons or 1 epsilon or 2 epsilon, because how many ever epsilons are there? 2 or 3, it is simply 1 epsilon, right? Now capital A on 0, where is it going? Capital A itself. Check this, capital A on 0 is going to capital A itself, and now capital B on 0 is going to capital C. Check this, capital B on 0 is going to capital C, and capital D on 0 is going to capital D itself. And again you have to find out epsilon closure. What is epsilon closure of A? Same, it can reach A, it can reach B, as well as it can reach D. What is epsilon closure of C? C will reach only C and not anything else. What is epsilon closure of D? D will reach only D. Therefore these are the states that should be present in this particular entry in the final NFA, right? What are the states? A, B, C, D. Therefore I am going to write it as A, B, C, D. Can I write these many states? Yes, obviously I could write, because it is NFA. Therefore any transition can be, contain any number of states, or it can even contain 5. Okay. Next I want to fill this row. What is this row? Capital A on 1. So again we are going to write the same way. Capital A if I have to find out on 1, I am going to write it as epsilon star 1 epsilon star. What is capital A on epsilon star? Capital A on epsilon star is I can go to A, B as well as D. Only I am looking at epsilon. A, B and D. What is capital A on 1? Capital A on 1 is, it doesn't have any move, therefore it is 5. What is capital B on 1? Capital B on 1, it doesn't have any move, therefore it is 5. What is capital D on 1? Capital D on 1 is capital D itself. And what is epsilon star of D? D. So D is not going anywhere on epsilon except D. Therefore here I have to write D. Singleton set. Now what about B? In state B, I have to discuss about B on 0. Now I am in capital B and I have to discuss about 0. So I have to write epsilon star 0 epsilon star. Where does B go? Only on epsilons. It will either go to B directly or it will go to D. So it is going to B and D. Fine. And what about on 0? B on 0 is going to C, D on 0 is going to D itself. What is epsilon closure of C? Where is C going on epsilons? Only to C. What is epsilon closure of D? Where is D going on epsilons? Only D. Therefore I have to write CD here. What about B on 1? B on 1. This part is going to be same. Fine. Now what about capital B on 1? Capital B on 1, it doesn't have any move. What about capital D on 1? Capital D on 1 is going to have one move, which is capital D. What is epsilon closure of D? Simply D. Therefore write it as D. What happens to phi? Phi is nothing but is not contain anything. So how can you say that it can go somewhere on nothing, from nothing, nowhere? So we are not going to write anything for that. Okay. Next one, C. C on 0. I'll be here epsilon star 0 epsilon. C on 0 is nothing but, C on epsilon star is nothing but epsilon, C, and C on 0 is, it doesn't have any move on 0. Check it. C doesn't have any move on 0, therefore it is 5, and therefore the outcome is 5. So what should I write here? C on 0 is 5. What about C on 1? C on 1. Find out C on epsilon star or epsilon closure of C. So C, epsilon closure is C itself. And what about C on 1? C on 1 is going to B. C on 1 is going to B. And what about epsilon closure of B? So it can even go to B as well as D. Therefore I have to write it as B, D. What about D? Again here discuss the same things. D, epsilon closure, find the epsilon closure of D, and then find out the transition on 0, and again find the epsilon closure on D. Fine. So what is epsilon closure of D? From D I can reach only D on seeing epsilon, so I cannot reach anyone of any state other than that. And what about D on D? It is simply D. And what about epsilon closure of D? It is simply D. Therefore it is going to be D. Fine. And what about D on 1? So again find the epsilon closure of D and then find the transition on 1. So what is epsilon closure of D? Epsilon closure of D is simply D. And what is D on 1? D on 1 is simply D itself. And what about epsilon closure of D? Simply D. Therefore this is again D. So this is the NFA for the given epsilon NFA. Now let's draw the transition diagram for the same thing. So how many states are there? We have only 4 states. So the main difference between conversion of NFA to DFA is, when I was converting NFA to DFA, the number of states they have increased, right? And here when converting epsilon NFA to NFA, the number of states are not going to increase, number of states are going to be same. Fine. So let's start with this: capital A, capital B, capital C, capital D. So initial state is definitely A, that you know. Now the question is, what is the final state? So when we are converting epsilon NFA to NFA, the final states are going to increase. So whatever state that can reach the final state only on epsilon is going to be final state. Again, if I can reach the final state from some state by seeing only epsilons, these states are also going to be final states. So in this given example, in this given question, let me draw the NFA same like epsilon NFA. A, let me draw B here, and let me put C here, and let me put D here. Okay, so if some state can reach the final state only on seeing epsilon, then that state is going to be final state. So in this case, B can reach D only on seeing epsilon, therefore B is going to be a final state also. D is already a final state, now B is a final state. Now see this, capital A can reach capital D only on seeing epsilons, therefore capital A is also going to be final state. So remember this, number of states are same, that is the first one, number of states are same. And second point is, initial state is same, true. And the third point is, the number of final states may increase depending on, if a state is going to reach the final state only upon seeing epsilon, then even that state is considered as final state. Since B can reach D only upon seeing epsilon, you can even say B is the final state. And A can reach D only upon seeing epsilon, so you can say that A is also a final state. Therefore A and B are also final states. And all the remaining transitions you can take from this table. So see this, capital A on 0, what is it doing? On 0 it is going to be in capital A, as well as it is going to B, as well as it is going to C, as well as it is going to D. NFA, right? Next, A on 1, where is it going? A on 1 is going to D. Fine. Next, B on 0, where is it going? B on 0 is going to C as well as D. B on 1, where is it going? It is going to 1, D. Next, C on 0, it has no move, and then C on 1. C on 1 is going to BD. C on 1 is going to, one is B, other is D. D on 0 is going to D, 1 is going to D itself, which means D is going to be 0, 1. So this is the NFA for the given epsilon NFA, right? So we shall revise what we have seen now. First of all, we are given a epsilon NFA. What is the main difference between NFA and epsilon NFA? Only difference is we have epsilon most. If you look at the transition table, NFA is going to contain a Q cross sigma, which means from a state on seeing an input, I may go to many number of states or no state or one state. That is true. But then if you look at epsilon NFA, I can even be from some state and then looking at nothing, which means epsilon, I can go to any number of states. So only difference is epsilon is added. So once you have found out this, now we have to construct the state transition table. So in order to construct this state transition table, we need a property called epsilon closure. What is epsilon closure? Epsilon closure is nothing but set of all states which can be reached from some state is going to be epsilon closure of that state. If I say epsilon closure of A, it is nothing but set of all states reachable from A. Then if I have to fill some row, fill some entry, then you have to write like this. If I have to fill capital A on 0, I have to write epsilon closure, which is nothing but I have to find epsilon closure of A first, and then whatever I get I have to find transition on 0, and then whatever I get I have to find epsilon closure again. So this is the final. So whatever I get here I am going to write here, right? So this is how we have to construct the NFA. Let's start with an example. Again same, we want to convert epsilon NFA to NFA. Okay, so let's start with this. Now let us say the language is A star, B star, C star, capital A, capital B, capital C. Okay, so in order to convert this epsilon NFA to NFA, I have to construct the transition table. Transition table is going to look like this: capital A, capital B, capital C. Okay, so inputs are A, B and C. Fine. So I have to find out what are the transitions on capital A on small a in case of NFA. In order to find it out, I'll write like this. I'll find epsilon closure of A first, and then A, and then epsilon closure. What is epsilon closure of A? What are all the states which I can reach from capital A only on seeing epsilons? One is A, other is B, and other is C. Fine. And what are the states which I can reach? Okay, and then it is small a. On small a can reach A, and what about B and C? B and C will stop there. They will die. This is called dead configuration, right? So they are not going anywhere. They will die. What about epsilon closure of A again? Epsilon closure of A is A, B, C. Therefore, this entry is going to contain A, B, C. Fine. And now we have to find out what happens on B and what happens on C for capital A. So everything remains same till here. Now I have to find out what happens on B. Fine. So capital B on small b, capital A on small b is going to 5, which means it is going to die, and capital B on small b is going to capital B itself, and capital C on small b is going to 5. What about epsilon star? So capital B on epsilon star is going to, which means epsilon closure, it is going to B, and one more thing is capital B on epsilon is going to C. Therefore here I am going to write it as B comma C. Fine. And now what happens on C? What happens on C? Capital A on C is going to 5, because capital A doesn't have any move on C, and capital B doesn't have any move on C, it is 5, and capital C on C is going to capital C itself, and epsilon closure of capital C is capital C. See, this is capital C and this is small c. Fine. And next thing is I will discuss about capital B. Capital B on small a. So what is epsilon closure of capital B? Epsilon closure of capital B is, one is it will contain B itself, and the other is it will contain even C. So B and C are the epsilon closure of capital B, and capital B on A is 5 and capital C on A is 5. Therefore it is going to die there. So capital B on A, it doesn't have any moves. Now capital B on B. Now what about capital B on B? Capital B on B is going to be capital B, and capital C on B is going to die 5, And what about capital B, epsilon closure of capital B? Epsilon closure of capital B is going to contain one is B as well as C. B and C, that is epsilon closure of B. Therefore, I am going to write it as BC. And capital B on C. Capital B on C is going to be, capital B on small c doesn't have any mu, therefore it is going to be 5. And capital C on C is going to be capital C itself, and epsilon closure of C is going to be C. Therefore, I am going to write it as C. What about capital C? Now, capital C on A, capital C's epsilon closure is C itself, and C on A is simply 5. Therefore, it is going to die 5. I should not write 5 like this, right? I should be writing 5. 5 is nothing but empty set, right? I should not include 5 inside a set. It means that it is a singleton set which is containing an element 5. So that is wrong. Fine. Next thing is capital C on B. What is capital C on B? Epsilon closure of C is C itself, and capital C on B is going to be 5. Therefore, everything is going to die, empty set. What about C on C? Epsilon closure of C is C, and C on C is going to C, and again epsilon closure of C is C. Therefore, this is it. So, if you draw the NFA for it, NFA will look something like this: capital A, capital B, capital C. On small a, it will either be here, or it will go to B, or it will go to C. And on small b, it will go to B and C. B and C. And on C, it will go to C. Next one, B. Capital B on small b is going to BC. B, B. And capital B on small c is going to C. BC. What about capital C? Capital C on A doesn't have mu, capital C on B doesn't have mu, but capital C here it will have mu, which is C. Fine. So this is how the NFA has been constructed. Now tell me, what about the final states? Number of states are going to be same. If I convert epsilon NFA to NFA, number of states are going to be same. What about the final states? So here let us assume that here the final state is C. In the original diagram, final state is C. Then whatever states can reach the final state, only on epsilon is going to be final state. So C is going to be final state definitely, and whatever states which those can reach the final state just by looking epsilon, they have to be included. If you look at B, it can reach C just by looking epsilon, therefore B has to be final. And if I look at epsilon on A, then I am going to reach the final state, therefore A has to be final. So this is the NFA. We constructed the NFA for the given epsilon NFA. And now you will understand that since we have already constructed a DFA, see, we have converted NFA to DFA, sorry, epsilon NFA to NFA, and we know that we can convert NFA to DFA. Therefore, you can know that I can convert epsilon NFA to DFA. So all the finite automators are equivalent in power. This is the final answer. Now let's just summarize what we have seen till now. So till now we have seen many kinds of finite automators. I can just write them like this: finite automators. We have seen various kinds, right? So one is finite automators with output and finite automators without output. And with output we have seen Murray machine and Mealy machine, and without output we have seen one is DFA, other is NFA, and other one is epsilon NFA. And we have even seen that, we have shown that every DFA is an NFA by definition. Depending on the transition function, you can find out that every DFA is NFA by definition, and every NFA is epsilon NFA by definition. And we have shown how to convert epsilon NFA to NFA and how to convert NFA to DFA. Therefore, we can say that all these are equivalent. And we have shown you how to convert, we have seen how to convert Moore machine to Mealy machine and Mealy machine to Moore machine. Therefore, both Moore machine and Moore machine are equivalent, right? And these two can even be compared, but then it is not required. Even the power of both of them is same. If the output has to be, if you want some different output, you can designate some state in the DFA and then you can just mimic it. But however, everything is same. So till now we have seen all the finite automatas possible, all these kinds. Now you should ask me one question, or one natural question. The question is, can we accept any language using a finite automata? Which means, given any language, can I construct a finite automata and accept it? That is the natural question, right? So we have seen lots of languages for which we have constructed finite automatas. Now the question is there any language for which I cannot give finite automata? Let me take an example. Let us say a power n, b power n such that n is greater than or equal to 1, which is infinite language. So the language is a set of all strings which are containing equal number of a's and b's, where a's should occur always b's. Okay, let me construct a DFA and then discuss whether it is possible or not. Now, language, let me enumerate it. It is AB, AA, BB, AAA, BBB, so on. So let me take the smallest string and give the skeleton. Skeleton is going to be simply A, B, and accept it. If I get a B, I should not accept this string. Therefore, this is the dead state. And if I see any number of A's, I'll be waiting for B's. And if I see any number of B's, I'll be accepting it. If I see a which means after a B, A is coming, I'll be killing it. So you might think that this is the DFA which accepts set of all strings of this. Maybe if you even have doubt, you can take an example and trace out. Let us say AB. On seeing AB, I'll be going to A and then B, final state. Yes. On seeing AA, BB, A, B, B, final state. Yes. On seeing AAA, BBB, A, B, BB, yes, final state. So all these strings which are there in the language are accepted. Therefore, you might think that for this language, this is the finite automata. But the problem is, if I take AAB, this is the string not in the language. Now check this, B, accepted. So even this string is accepted which is not there in the language. Therefore, it is there is some problem in the DFA. The problem is this: we are able to check whether all the B's are followed by A's and there is no A after a B. We are only able to check that, but then we are not able to keep a count of number of A's and then compare it against B's. So the keyword is, we are not able to count using a finite automata. What kind of counting? I can count 2 A's, I can count 3 A's, or I can count finite number of A's. But if I have to count infinite number of A's, I need infinite amount of memory. So finite automata, if it requires infinite memory, see, finite memory, yes, it is possible. Why? Every state can remember something, therefore it is having some kind of finite memory. But if the finite automata is asked to remember or if a finite automata is asked to have infinite memory, in this case, if it has to count and store infinite number of A's, it is not possible. Therefore, there are some languages for which always constructing a DFA or NFA or in fact a finite automata is not possible, and this is one such example. The reason is, a finite automata doesn't have infinite memory. Therefore, we want a finite automata plus infinite memory which is a more powerful automata, which is also called as push down automata to accept this. What is push down automata and what is the languages? We shall discuss it now. Okay. So we have seen that there are some languages for which finite automata cannot be given, which means we need some powerful machine in order to accept such languages. So what are these languages and how can we categorize this? So I can write something like this. Let us say the languages for which we have given finite automatas are the languages which we have seen till now, for which we have drawn finite automatas, either a DFA or NFA or epsilon NFA or Mealy or Mori machines, all fall in a class called regular languages. So you take any language we have taken till now, they are all falling in language called regular language. And there is even a powerful class of languages which will include regular languages, which is called push down context free languages. Context free languages. And there is even a powerful class of languages which includes this context free languages, which is also called as context sensitive languages. Regular language, context free language, context sensitive language. And there is recursively enumerable sets, RES. Recursively enumerable sets, context sensitive languages, context free languages and regular languages. So if you have to see some example, a power n such that n is greater than or equal to 1 is regular language, right? And a power n, b power n such that n is greater than or equal to 1 is context free language. And a power n, b power n, c power n such that n is greater than or equal to 1 is context sensitive language. And a power p such that p is a prime number, is recursively enumerable sets. Don't worry, we are going to look at all these languages one by one, but for now just think that there is a class of family of languages which is called regular languages, for which we have given finite automata, and there is a family of languages which is called context free, context sensitive and recursively enumerable, and they are all placed within one another. Now for the class of regular languages, the machine which was able to accept it is finite automata, and for the class of context free languages, the machine which was able to accept it is push down automata, and for context sensitive languages, the machine which will be able to accept it is called linear bounded automata, and for recursively enumerable sets, the machine which will be able to accept it is called a Turing machine. It's called a Turing machine. So what is a regular language and what are the properties of regular language? We shall study them at depth, and then we shall take context free languages, and then we shall take context sensitive languages, and we shall take recursively enumerable sets. So even there is one interesting thing. For any language, let us say we have taken regular language, that can be generated by something called as a grammar. So for the class of regular languages, there is a grammar called regular grammar, and for class of context free languages, there is a grammar called context free grammar, and for the class of context sensitive languages, there is a grammar called context sensitive grammar, and for the class of recursively enumerable sets, there is a grammar called unrestricted grammars. So there are some family of languages. These are the family of machines which will accept this family of languages, and these are the family of grammars which will generate this family of languages. Now let's take only regular languages, and we have already discussed about finite automata. Let's discuss the other parts too. Then we shall go to context free, then we shall go to context sensitive, then we shall go to recursively enumerable sets. Now let's talk about regular languages in depth. We have a class of families which we have seen till now, set of all strings of length 2, set of all strings of length less than or equal to 2, greater than or equal to 2, and then we have seen many other problems starting with A, ending with B, starting with A, B, and then we have seen binary numbers which are divisible by 2, 3 and all these are nothing but regular languages. And for a class of language there will be something called acceptors. Acceptors are nothing but some mathematical representation to which if you give a string, it will say either yes or no. Yes, this string is in the language or the string is not in the language. That is also called as acceptor. So for regular languages, the acceptors are nothing but finite automatas. And we have seen two types of finite automatas, right? So with output and without output. Right, and with output we have seen Mealy machines and Murray machines, and without output we have seen DFA, NFA and epsilon NFA. That is all done, okay, and all these we have proved that everything is equal and same. Now there is something called generator. So generator means given a language, it will generate all the strings in the language. Acceptor means given a string, it will say yes, this string is there in the language or not. Let us say if the language L1 is set of all strings starting with A, AB, so on, right? Then given a string A, B, B, if I ask whether this is in this language or not, then I can use acceptors which will say yes or no. But if I want to generate the entire language, which means if I want to enumerate all the strings, I'll just give I'll not ask about one particular string. I want about all the strings present in the language. Then I can use generators. Generators are nothing but grammars. So in case of regular languages, the grammars which accept regular or which generate regular languages are called regular grammars. Regular grammars. And regular grammars are of two types. One is right linear grammar and other is left linear grammar. So remember this, regular grammars generate all the regular languages. One is right linear grammar and left linear grammar. What is a linear grammar and all, we shall see later. And other class and other thing which can be associated with a regular languages is something called as representator. So regular languages can be mathematically represented by some expressions called regular expressions. These are the mathematical expressions using which we can represent a regular language. So we have already seen what is a acceptor, which means finite automata, and now we'll see what is a representer and how we are going to represent a regular language using these representers. Okay. Let's talk about regular expressions. So regular expressions are the representations of the languages which are exactly accepted by finite automatas, or if you can take any language which is accepted by a finite automata, we can represent it using a regular expression. So we shall discuss what is regular expression. Regular expression contains three operators. Okay. So one is union, which is also called as union operator, and other is concatenation. So it is called concatenation operation, and the third one is star, which is called as clean closure operation. Clean closure operation. So we have three operations in regular expressions. What is a regular expression is, point number A is, if phi is the empty set, this is a regular expression, phi is the empty set and epsilon is the empty string. These are both regular expressions representing, phi represents empty set like this and epsilon represents the language like this. If this is the language, this is the representation. If this is the language, this is the representation. Phi and epsilon and sigma. Sigma, A belongs to sigma, is also a regular expression. So understand this. One is I can write phi as the regular expression, it represents the language empty set. I can write epsilon as the regular expression, it represents the language which is containing only epsilon, and any input symbol a which belongs to sigma is also a regular expression. If I write small a, it represents the language like this, a. If I write small b, it means that the language is b. Okay, so these are also called as primitive regular expressions. Primitive regular expressions. Fine. And second point is, if I take any primitive regular expression, let us say R1, and if I take any other primitive expression R2, and if I apply any of these or any number of times, R plus R is a regular expression, R1 dot R2 is a regular expression, and R1 star is a regular expression. See this, primitive regular expressions are phi, empty set, epsilon, which contains only null string, and then any symbol of the input is nothing but primitive regular expressions, and then any regular expression which is union of two regular expressions is a regular expression, concatenation of two regular expressions is again, and this one. And you use these two, a and b, any number of times. You can use both the rules a and b any number of times, and whatever you get is also a regular expression. So understand this, phi, sigma, phi, epsilon, and any symbol which belongs to sigma is primitive regular expression, and then any operator applied to these primitive regular expressions are again regular expressions, and you can take a and b and apply them as many times as possible. Whatever you get is a regular expression. So I'll tell you some basic languages which can be formed using regular expressions. First one is phi. If this is the regular expression, then the language is empty set. If, let me say, epsilon, if this is the regular expression, then the language is containing epsilon. If a is the regular expression, then the language is this. If I write a star as the regular expression, then the language is, see, whenever I write star, it means that in place of star you can put any number including 0. In place of star you can put any number including 0. So if I put 0 here, I get epsilon. A for 0 is, which means string of length 0, which is epsilon. If I put 1 here, I get a. If I put 2 here, I get a, so on. And a plus. A plus is a special operator which is nothing but a concatenated with a star or a star concatenated with a. It is nothing but, in place of plus you can put any number except 0. So starting number is a 1, so it is a. If I put 2, it is a, so on. That is the main difference between these two. If I write a plus b star, it is nothing but set of all strings possible over a comma b. How I can get it is, you put 0 here in place of star, I get epsilon. If I put 1 here, I get a comma b. If I put 2 here, I get set of all strings of length 2, which is a, ab, ba, bb. If I put 3 here, I get set of all strings of length 3. If I put 4, set of all strings of length 4. If I put n, set of all strings of length n, so on. Therefore, this represents the set of all strings possible over a comma b. So this is what is the basics of regular expressions. Now we shall solve some problems and then you can understand it better.